All right, let's talk about three words you probably hear all the time if you're in the world of data or AI: graphs, networks, and knowledge graphs. They sound kind of the same, right? But they're not. They actually tell this really cool story about how we've gone from drawing simple connections to building systems that can actually understand meaning. So, what's the deal? Are they just fancy synonyms? The short answer is nope, not at all. Think of them as layers in a journey, with each one building on the one before it. And by the end of this, you'll see exactly how that works, and more importantly, why it matters so much. So, let's dive in. We're going to start at square one, the absolute foundation of it all, the graph. Before we add any real-world data or complex meaning, we have to understand the blueprint. The graph is pure mathematical structure. And the whole field pretty much started with this famous brain teaser from way back in 1735. The city of Königsberg had 7 bridges, and people were obsessed with this question. Could you go for a walk and cross every single bridge exactly one time? A brilliant mathematician named Leonhard Euler heard about it, and he had this incredible aha moment. He realized the layout, the length of the bridges, none of that mattered. The only thing that mattered was the pattern of connections. So he turned the land masses into dots and the bridges into lines, creating the world's first graph. He not only proved the walk was impossible, but he basically invented a whole new branch of math in the process. So what is a graph, formally speaking? It's surprisingly simple. It's just a collection of vertices, you can just call them points, and a collection of edges, which are the lines that connect those points. That's it. Seriously, it's all about pure structure, the raw pattern of how things are connected. It's the universal language for talking about relationships. Now, right away, we can add a simple but crucial bit of information. Are these connections a two-way street? An undirected graph is for mutual relationships, like being friends on Facebook. The connection between me and you is the same as the connection between you and me. But in a directed graph, the relationship has a direction. Think about following someone on Twitter. You can follow them, but they don't have to follow you back. The arrow only points one way. Okay, so this mathematical blueprint is incredibly powerful. It's like the basic grammar of connection. But what happens when we take that grammar and start using it to describe the messy, complicated, real world? Well, that's when we get a network. This is where we take that abstract idea of a graph and anchor it in actual observable data from the world around us. So here's the key difference. A network is a data-rich graph. The vertices get a new name, nodes, and now they represent real things, people, companies, cities. The edges become links, and they represent real interactions, friendships, transactions, flight paths. We can even load them up with data, like your age or the flight time. The abstract blueprint has just become a map of something real. And our understanding of these networks really evolved over the decades. At first, scientists kind of assumed that connections were basically random. But as they started mapping more and more real-world networks, they found something mind-blowing. Real networks are not random at all. They have hubs, like a major international airport or a superstar celebrity with millions of followers. It's this rich-get-richer phenomenon where popular things just keep getting more popular. And it turns out this is a fundamental law for almost every network we see. And once we have these data-rich maps, we can analyze them with some seriously cool tools. We can use math to find the most influential person in a social circle. We can run algorithms to find hidden communities or clusters. We can analyze the whole structure to understand how a system is organized. We're not just proving abstract theorems anymore. We're making scientific discoveries. But here's the catch. A network is great at showing us that a connection exists, but it has no idea what that connection actually means. A computer sees a line connecting Steve Jobs and Apple, but it doesn't understand the relationship is co-founded. That meaning is still all in our heads. So what if we could teach the machine? And that brings us to the top of the pyramid, the final and most powerful layer, the knowledge graph. This is where we stop just connecting dots and start giving those connections real, machine-readable meaning. The secret sauce of a knowledge graph isn't just a node and an edge. It's a special unit called a triple. It's basically a simple sentence with 3 parts: a subject, a predicate, and an object. So instead of a vague line, we now have a specific fact. Leonardo da Vinci painted the Mona Lisa. See that? The edge itself, the predicate, now has a name and a meaning. And this idea, well, it's the fulfillment of a vision from the inventor of the World Wide Web himself, Tim Berners-Lee. He dreamed of a semantic web, where it wasn't just pages linking to pages, but data linking to data in a way that machines could actually understand. A knowledge graph is really that dream made real. So you might be asking, how does a machine actually know what painted means? It learns from something called an ontology. The best way to think of an ontology is like the official rulebook for the knowledge graph. It defines all the categories, like person or artwork, and all the possible relationships, like born in or created by. It's this formal set of rules that lets a computer start to reason about the world. And you interact with these all the time, probably without even thinking about it. That little info box that pops up in a Google search with direct answers, that's a knowledge graph. When your streaming service recommends a show because it has the same actor you like, knowledge graph. They're also a huge deal for AI because they allow a system to explain why it made a choice, which is absolutely crucial for building trust. Okay, let's zoom out and put this entire evolutionary journey together. We've gone from pure, abstract shapes to a rich web of meaning that machines can actually understand. Look at how it all stacks up. The graph is pure math, focused on proofs and algorithms. The network grounds that in reality, focusing on scientific discovery and patterns. And finally, the knowledge graph adds that crucial layer of meaning, so an AI can focus on reasoning. The question we're asking evolves, right? From what's the structure, to what are the patterns, to finally, what is true? So if there's one thing you take away from all of this, let it be this simple progression. The graph gives us the universal syntax, the grammar of connection. The network populates that syntax with real-world data, and the knowledge graph layers on the semantics, the actual meaning. Syntax to data to semantics. That's the whole journey right there. And make no mistake, this journey isn't just some neat academic exercise. This evolution is the engine that's driving the next generation of AI. It's how we're building systems that don't just calculate, but can actually reason, explain themselves, and understand the world in a much deeper way. Which leaves us with a pretty big question to think about. As we keep pushing down this path, from just mapping simple lines to defining deep meaning, how is that going to shape a machine's view of our reality? What does it really mean for an AI to not just process the world, but to have a structured, reasoned understanding of it?